Okay. All right. So let me finish the lecture with the following result. I wanted to prove something previously, but we didn't have much time, so I had skipped it about uniform convergence and differentiability of functions. Remember, we proved that if I have a sequence of functions converging uniformly on a closed interval, okay, so these functions are defined on a closed interval and they are converging uniformly. If all of them are integrable, then the limiting function is integrable and so on. We have an analogous statement for differentiable functions. Let me state and prove that one. And let's finish this class with this result. So assume that Fn is a sequence of functions uh, on some interval like this. Okay. Uh, uh, Further assume that the followings. Okay. I assume that each Fn is differentiable and is differentiable, and Fn prime is also continuous. So they are continuously differentiable. Okay. Second, there is okay. There is some x0 in the interval AB, so that the sequence of real numbers of real numbers Fn of x0 is convergent. I don't assume Fn's converging to a function uniformly. I only assume that there is a point, and at that point, if I evaluate these functions, the sequence I obtain is convergent. And I also assume this. The sequence of functions, this function sequence, the derivatives, these are also continuous by assumption, is uniformly continuous, uniformly convergent to some f. Okay. Then the conclusion is this. Then uh, Fn converges, okay, converge to some g, let me say, converges to some function, to some differentiable function, let me say, f, so that derivative of this function is g of x. Okay. Well, it's kind of strange that, we have so many assumptions for this conclusion, but when it comes to differentiability, things are more complicated, okay, compared to integrals. That's why we need all these assumptions. Now you will see in the proof that we really use all of them. Maybe some of them might be weakened, but you will see that we will use all of them. Okay, let's see how we prove this proof. So let me look at this theorem one more time. I have a sequence of functions. We assume each one is continuously differentiable. So they are differentiable and their derivatives are continuous. The functions evaluated at a single point. There is a single point x0. Of course, there might be more than a single point, but there is at least one such point, so that this sequence of real numbers is convergent. And we assume that the derivative functions are continuous, uniformly convergent to some function. And since these are all continuous by assumption, the limiting function is also continuous, of course. Then the conclusion is that then the original sequence Fn converges uniformly to a differentiable function, and the derivative is just the limit of the derivatives. Okay. Okay. Well, note that okay. Note that uh, we have the following: f uh, each fn x satisfies the following: fn x minus fn x0, right? X0. Since f is continuously differentiable, this is just equal to x0 to x fn t dt, and therefore, and hence, fn x is equal to fn x0 plus x0 to x fn t dt. Okay. Sorry, fn prime, I should say, right? The derivative. This is just the fundamental theorem of calculus. I just rewrote it. So, therefore, hence, okay, therefore, the distance between f and x and f m x is what? So I have this fn x0 plus x0 to x fn prime t dt minus fm x0 minus x0 to x fm prime t dt. All right, and this can be written as, okay, so I group these two terms and these two. So we have what? I have fn x0 minus fm x0 plus integral x0 to x fn prime t fm prime t dt. All right. Well, this sequence is convergent, right? Fn x0 is convergent and Fn primes are convergent. Therefore, I can make all of them smaller if I want. So, given epsilon positive, uh, choose, okay, since this sequence is convergent, uh, there is some n1 so that uh, this is convergent, therefore it is Cauchy, right? So that m and n larger than n1 implies f n x0 minus f m x0 is less than epsilon over 2. All right. Also, similarly, this sequence fn prime x is Cauchy, and thus there is some n2 so that m and n are larger than n2 implies supremum metric. So fn t or fn x, fm prime x, fm prime fn prime x, fn prime x is less than, well, okay, I want this to be less than epsilon over 2, so I want this to be less than epsilon over 2 times b minus a. Right, AB is a closed interval. I look at the length of that. So, in particular, we have what? The okay, both x and x0 are in this interval, and thus this integral f n prime t minus f m prime t dt is what? This is less than, right, this integral I take absolute value inside the integral, but this gadget is less than this number, whatever it is less than epsilon over 2 times b minus a, and this is equal to, this is a constant, so I can just compute this integral as follows. So this is just x minus x0. Okay. Here, of course, I assume x is larger than x0. Yeah, but okay. Maybe I should put absolute value here. Here, x is larger than x0, but sometimes I can choose x. Right, here is a, b, x is here, x 0 and x like this. If x is larger than this is positive, if it is less than x0, then this will be negative. But if I just, take absolute value, I will get this. Okay, so in particular, this distance, whatever this is less than b minus a, of course. So this is less than epsilon over 2. So what I have, both this term and this term are less than epsilon over 2. This is less than epsilon over 2 if the indices m and n are larger than n1, and this is less than epsilon over 2 if m and n larger than n2. So I choose my n0 to be the maximum of n0, n1 and n2. Then if m and n are larger than n0, then uh, the distance between f and x and fmx is less than, right? This is less than epsilon over 2. This is less than epsilon over 2. Which is epsilon. So let's see what we have obtained. Given epsilon positive, I found some n0, so that if m and n are larger than n0, then this distance is less than epsilon. So this implies what? Hence the sequence uh, f and x is Cauchy in the metric space CAB with the absolute supremum metric. Since this metric space is complete, since CAB D sup is complete, f and x converges to some f in this space. So we have found f, right, as we claimed here, fn converges to some function, and we know that it is continuous, but we claim more. We claim that this limiting function is convergent, and moreover its limit is equal to the limit of the derivative functions, right? These derivatives converges to g, and I claim that the derivative of the limit of fn's is equal to that g. All right. All right. So sorry. Now, uh, okay. Note that f of x is equal to limit of f and x, right? As n goes to infinity. uh, and and uh, okay, f of x minus f of x0 is equal to limit as n goes to infinity fn of x minus fn of x0, and I can write this as what? This is nothing but the from the uh, fundamental theorem of calculus. This is x0 to x f n prime t dt. However, we know what fn's converges to fn primes. This converges to g t uniformly. We know this uniformly on AB. Therefore, uh, this integral, I know that this is just integral of x0 to x gt dt. Right. Yeah. And what is this? This is just uh, uh, so what we have seen is then okay. What is this? This is just g of x minus g of x0, right? Yeah, or actually I have this. Hence, we have what? F of x, sorry. Hence, f of x is equal to f0 plus integral of x0 to x gt dt, where gt is continuous. Is a continuous function. Why is that? Because it is the limit of fn primes, and fn primes are continuous. Therefore, the limiting function is continuous. But again, by the fundamental theorem of calculus, then this function, right, this thing is differentiable, and the derivative is just gx. Hence, thus uh, again by the fundamental theorem of calculus. Theorem of calculus. Fx is differentiable and f prime x is equal to what? Derivative of this, of course, this is a constant, right? So its derivative is just 0 plus derivative of this. Maybe I should write d dx. Okay, let me write it this way. d dx of f of x0 plus d dx of x0 to x gt dt. Yes, this is a constant, so derivative of the constant function is 0. And what about this? This is just g of x. So this gives us, so f is differentiable and its derivative is equal to g. So that f of x is differentiable. With derivative g of x. And this is this finishes the proof. Okay. Any questions so far? So this is a theorem about differentiability of sequence of functions. Okay. Compared to integrability, it is more involved. We have to assume several things, but you see, we used all of them almost. You can apply this to, of course, power series. Okay, power series converges uniformly on closed intervals contained in the convergence of in the interval of convergence, and there you can use this, and you take derivatives of power series using this theorem. So maybe I should do this as an application, as an example. Okay, let this thing be a power series with a radius of convergence r positive. Okay, then okay, then for any AB contained in this interval x0 minus r, x0 plus r, okay, the series converges uniformly. Okay. We proved this using Weierstrass M test. So if I let Fn to be this function, let Fn x to be an x minus x0 n, then okay, then each Fn x is differentiable, or yeah, okay, let me consider this converges uniformly. I know this, but we have also the following. The series, let's say an over n plus 1. Okay, this one converges, has the same radius of convergence, and thus it converges uniformly. Okay. Now let f and x to be this function, an over n plus 1 x minus x0 to the power n plus 1. Then then fnx is, of course, continuously differentiable on this interval on AB with derivative. What is the derivative of this function? Well, it is just an times x minus x0 to the power n. And by assumption, this series is convergent, right? If I write it as a series, then it's convergent. Okay. Moreover, this is convergent, it converges uniformly on AB compact set, and also moreover, okay, finally, uh, limit of fn prime, which one was that? Okay, what was the assumption? Yeah, okay, yeah, this one. Okay, so I want this thing, the series f n x0. at a single point. What is this? If I plug x0 here, of course, we get just 0, right? Is convergent. So I have what? I have a series of functions. Each element is continuously differentiable. And when I take the derivatives, I get a series which converges uniformly. And the original series is convergent at one point. I can choose this point anything I want. In particular, if I plug x0 here, I get 0, so it is convergent. Therefore, we can use the previous theorem. Hence, by the previous theorem, the series, which series? This series, f and x and from 0 to infinity, which is nothing but, what was this? This is a n over n plus 1 x minus x0 to the power n plus 1 is uh, uniformly convergent. I knew this, convergent, and it is differentiable with derivative. What is the derivative of this? So x derivative of this, by the theorem, it is nothing but you just take the derivative of each function. So it is this. Okay. And this means what? Derivative of this expression a n plus 1 x minus x0 to the power n plus 1 is equal to this gadget. What is this? This is just a n minus x0 to the power n plus 1 n. All right. So this means what? Whenever you give me a power series, I can differentiate it term-wise. Derivative of this is just you is just the function where you take derivative of each term separately. So in other words, you can take this derivative sign inside the summation. Okay. This is something really important. Okay. This allows us to integrate and differentiate power series term-wise. So this theorem, together with the one about integrals allows us to differentiate and integrate power series term-wise. Okay. Also, actually, this works not only for real valued functions, but also for complex valued functions. the same story holds. Nothing is different. Instead of real valued functions, I may consider complex valued functions. I can put suprametric for on those functions and so on. Indeed, the same holds for complex valued functions and power series. Okay, this is something you use in complex calculus, right? To prove several theorems, you probably use this theorem. All right, I think we may stop at this point. Sorusu olan var mı arkadaşlar?